So, first of all, quick recap from the last two lectures, which I'm sure you all saw. First lecture, we talked about applications of, like, prototypical applications of linear algebra. Most of the applications involve taking some sort of derivative of a thing, and when you have lots of equations and lots of variables, that ends up being a matrix of derivatives. So, typical example is, for instance, you have a bridge, and then for each part of the bridge, you've got some equation that talks about the forces balancing on that part of the bridge, and then you've got a bunch of variables for, like, lengths of things or forces on things. And then if you think about small changes to that bridge, you're going to be taking derivatives of each of the equations with respect to each of those variables. And then you get a matrix where each row is one of the equations, and each column corresponds to one of the variables. And that's like a sort of prototypical example of a thing where we use all our usual linear algorithms. Or similarly, if you're looking at a matrix of second derivatives of a scalar function, like a loss landscape, you want to look at curvature around a point. That's another typical place where we get a matrix, it's all full of derivatives. So that was first lecture, looking at applications, or typical use cases. Second lecture, we talked a bit about how to work with these matrices efficiently in code, in particular how to avoid actually explicitly computing these whole giant matrices of derivatives. We use implicit representations. Today, we're going to talk about, first of all, what typical matrices look like when you just go plot them, how to interpret that, and then how to use those sorts of structures when you find them. So, first thing for today, some patterns that you might see when you go look at a matrix. What do I mean by look at a matrix? I mean you call pie plot dot match show on your matrix M, or imshow. Imshow does the same thing. So, let's say I call pieplot.matchShow on my matrix, and my matrix looks like this. It's like a solid block of purple or dark blue or something. That's what I see. What does this mean? Yes?
It's either all the same color, or all the same value, or your scale is out of whack.
Either all the same value or my scale is out of whack, right. In particular, if they're all the same value, probably the value is 0. But how would I tell the difference between these two cases?
You can make sure your scale is in what? Oh, you could just like...
Look at your scale. There you go.
Doesn't it always be scale?
Get to that. So the next thing I would do, if I saw something that was all one color, was I'd call pieplot.colorbar. See my scale. And color of. And then there's two possibilities. Possibility 1 is that my color bar goes from 0 to 0. So, like, my color bar is just like, yep, all of these values are 0. I'm like, okay, now I know that my matrix is all zeros. The other possibility, slightly more interesting, is that my color bar goes from, like, some big number up here in red down to some small number down here in purple, and my entire matrix appears to be approximately there. What does that mean? Well, that means that somewhere in here, there's a few little red pixels hiding out, and there's a few little purple pixels hiding out, but the vast majority of my matrix values are like this middle value, right? In other words, this is telling me I have a sparse matrix. Probably what I did was I plotted a reasonably large matrix with like a few thousand by a few thousand, and there's like a handful of non-zero pixels in there, and the rest of it is 0. Make sense?
Yep.
So that's pattern number 1 that we want to look for, is you plot the matrix and it looks like basically one color, or if you zoom in, probably you'll see some little dots in there. All right, that's a sparse matrix. Great. What other patterns might we see? So keep a list over here. First pattern, sparsity. Second pattern. My cloth sample catalog. Second pattern you might see when you plot a matrix is plaid. What does plaid mean? Anybody besides Garrett? Garrett's seen a version of this stuff before. So.
Like some of your features were not like they were 0 or something. Some of your variables were 0.
Nope. Alright, fine, Garrett. Tell.
It's low rank.
It's low rank. There we go. Good. So if you take two vectors, you've got one vector like this multiplied by a vector like that. So you've got this big outer product of two vectors. And this vector, let's say if we graphed it, it would look something like that. And then this vector, if we graphed it, would look something like this. Then when we take the product of those two things, we're going to get something that has sort of like a big high stripe along where that peak is and a low stripe where that peak is. Along this direction, we're going to get sort of a high stripe in line with that peak and a low stripe in line with that valley. So we're going to get this like pattern of strong horizontal and vertical stripes.
This is like I would expect you'd usually see this if you have like some kind of privileged basis like this one. Because like trying to imagine, well, you have most like unitary transforms of a low rank would like not look plaid. Was my intuition?
No. So the nice thing about a low rank decomposition is when you have when I've got my big matrix equal to a low rank decomposition, I can apply some transformation to this thing. Let's like for instance, let's say I rotate it by r over here. Well, that's going to rotate this vector. And now I'm going to have like some different highs and lows in here, but I'm still going to get those strong like row patterns. Like whenever there's a high value in here, I'm going to get a high value down that whole row. Or conversely, for a low value in here, like if there's a value near 0 in here, it's going to be near 0 along that whole row. So you generally get that strong like plaid visual.
Okay. And is this like literally meant to be column vec, outer product, row vec?
Yep.
Is this like
you will get a similar visual if you have a few components.
okay?
So for instance, if you have like rank 3 or rank 4, you'll usually see something pretty similar. You'll get that distinctive plaid pattern. Make sense?
Sorry, did I understand that correctly? That like low rank matrices can always decompose like this, or?
Yeah, that's the definition of a low rank matrix. Is you can decompose it into something with a few columns times something with a few rows. Okay. All right. So those are the two main building block patterns that we're going to be talking about today, is sparsity and low rank. So most often when you go and call pyplot.matchshow, you'll see something that's either something that's a combination of the two. And usually one of the two will visually dominate. So most often what will happen when I call matchshow is either first I see a plaid pattern, and I'm like, okay, I can tell this is dominated by low rank components. What I'm going to do is calculate those low rank components. So for instance, do a singular vector decomposition and take like the top 5 or the top 10 or whatever singular vectors. And then I'm going to subtract those off. And after subtracting those off, I get one of these guys. And I got to zoom in on that, and like there's a sort of a sparsity pattern there. Or conversely, I go call pyplot.matchshow, and I see one of these guys. And I put up the color bar, and sure enough, there's sparsity going on in there. And then I will either subtract off the few sparse components, or just like limit them somehow, so that I can visualize what's going on with the rest of it, and it'll be clear that there's a low rank pattern left in the rest. So most often, what we have is a sparse plus low rank pattern. You have some sparse matrix, which I'll draw like this, plus a low rank matrix.
Most often in what context?
Pretty much any numerical context. Pretty much any numerical work you're doing, like the most prototypical thing that you most often run into is this sort of structure. And obviously that'll be, depending on what you're doing, that may be a better or worse approximation. For instance, if you're doing like engineering simulations, probably this will be an extremely good approximation. If you're working with a neural network, then there will be some non-trivial residuals, but it'll still be decent. But yeah, it varies based on the use case. All right, questions so far?
So when you're taking this outer product,
Mhm.
isn't your rank just 1?
If each of these is a vector, then yes, this will be rank 1. But it could be like maybe this has 3 columns in it, and this has 3 rows in it, for instance, and then we'll have rank 3.
Oh, okay. Sorry, I thought that was just that makes more sense. Yeah.
All right, let's talk about what these things correspond to conceptually. So, give me an example. Somebody give me an example of a system that you might want to like simulate numerically.
Bridge.
We did a bridge like 2
Oh,
times ago.
no physics.
Quadruple
I
velocity,
requested no
no.
physics
No.
examples.
No physics.
No.
Yes, basically no examples left.
That's left after
I'm a
physics.
mathematician / psychologist, so I want to hear something different.
Let's do brains.
Brains. All right, we're gonna do brains. So, let's say we're looking at a brain, and I'm not a neurologist or anything, so I'm just gonna make some stuff up here. But let's say we're looking at brains. In those brains, let's say we've got a big old matrix that's representing like each row is signals coming out of the neuron, and then each column is like signals coming in or something like that, right? First of all, presumably we're going to get a big sparsity pattern, right? Like neurons, a neuron connects up directly to maybe 1,000 other neurons, right? That order of magnitude, 10,000?
It's about 1,000.
About 1,000. All right, and you've got like a trillion neurons total on the right order of magnitude here.
You've got
86
86 billion.
86 billion. All right, so we're talking 100 billion neurons, and they each attach to about 1,000 others. So the vast majority of entries in this are going to be 0, because most of them aren't directly touching the others, right? You can get an extremely sparse pattern. But you may also see something like this sort of low rank thing going on. What sort of phenomenon would do that? Well, one thing that would give you a low rank component is if there's some sort of synchronized activity over a broad region, then you'll get like some small local correlations directly between neurons that are talking to each other directly or that are like one neighbor hop away. But then you'll also get some like long range correlations across a broad region.
Wait, so is this at a specific instant? What if like this neuron is like getting an action potential or something?
Mhm.
So and like
Think of
what are the
this.
things that
So
fit into
I was picturing this as some sort of correlation matrix.
it? Okay. So the correlation would simply be taken over time.
Over some
Okay.
short time. I don't know how people do this.
Okay. So like maybe we have some low rank components that come from like, well, what's needed by like the optic nerve or something.
Yeah,
Or-
so like sorts of things that you might have low rank components for. One would be if there's some broad synchronized pattern. Another would be
With
if,
harmonic motion?
yeah. Actually, people use that word in more than one way, so there's a way in which that can be used correctly here. But yeah, another possibility would be some sort of shared chemical component. So for instance, if you're flooding your brain with dopamine right now, that's going to be a big global component that shows up across everything all at once. So that sort of stuff is what a low rank component would do. For instance, that case of like flooding your brain with dopamine all at once, you're going to have a whole bunch of neurons that are dumping dopamine in there. That all basically gets added up and then broadcast to everything else.
So like if we have a correlation of the action potential matrix, and if we just imagine everything has an action potential continuously, then like everything you're just gonna like for like half the time, then no matter what is going on in the other half, you're gonna have some like positive correlation component across all of them that you can just like simply decompose. It's like, will
Yeah.
that just be rank 1 or something?
So this is the sort of typical pattern we see, is there's lots of little local activity, and then there's also like a few large global components, and you can sort of decompose into those two parts. And often, like you'll do this recursively at multiple scales, right? So, for instance, another common pattern we might see, maybe instead of just an arbitrary sparsity pattern over here, we have some blocks. For instance, block diagonal is a pretty common pattern, plus a low rank component. And then within each of these blocks, there'd be additional structure. So like if I go look at this block, maybe this also has its own little like sparse pattern plus a low rank component inside of it. Right? So like at different scales, you might get the same pattern recurring. Or another example of this in numerical PDEs, an operator we want to look at very often is the Laplacian operator. So you have something like 4 is all the way down the diagonal, and then -1 and -1 -1 directly above and below the diagonal. And then somewhere out here, there'd be another diagonal of -1s, another one opposite there. So this matrix form, first of all, is very sparse, obviously. But more interestingly, you usually want to look at the inverse of this matrix, because the typical case where it comes up is you've got some PDE, like del squared phi equals 0, for instance. Doing some sort of like electromagnetic thing, or a heat equation like del squared phi equals minus partial phi partial t. Is there a minus sign there? Is there a minus sign there?
Oh man.
You don't remember either. All right,
Sorry.
Maybe there's a minus sign there. Anyway, so like this is like a very typical PDE that you might look at describing like heat flow or electromagnetic fields. Yeah.
Ah.
And this is the matrix corresponding to that del squared operator. So what I usually want to do here is I've got my field over here, and I'm trying to invert this matrix to solve for that field, right? And then when I'm thinking about what the inverse of this matrix looks like, it turns out that one of the current best algorithms for solving that is something called a multi-grid algorithm, which is essentially doing this sort of thing recursively. You've got like some largest global components, and then you're sort of recursively breaking down into smaller decompositions like this. Make sense? Anyway, not expecting you to know all of that off the top of your head. The important point is this is like a very common pattern that we see all the time, and the interpretation is you've got some low dimensional global interactions, and then a whole bunch of local interactions that are sparse. Make sense? Good. All right, let's talk about how to utilize this. That's real quick. So, first typical thing you might want to do here. It's very easy if you have a sparse matrix to multiply it by some vector x, right? It's slightly less easy, but still like a thing there are standard libraries for, to solve sparse matrix times x equals y. Solve for x. So that's like more annoying, but you can plug it into a standard library and it'll work. What if I want to do the version of this with a low rank component added on? Turns out there's a handy trick for this. If you take any matrix M and you add a low rank component to it, I'm going to write this as M plus left times right. Or this is the tall one and this is the wide one. And then I want the inverse of that matrix. Turns out that matrix is itself a low-rank update of the inverse of M. So this is M inverse plus, let's see if I can do this off the top of my head. It's R L inverse times I think that's it. Don't quote me on that, but the more important thing is you can look it up on Wikipedia. Just Google, low rank update inverse formula. It'll tell you everything you need to know. And indeed, when I was doing lots of linear algebra on a day-to-day basis, that was the Wikipedia page, which I most often had to open up because I use it all the time, right? So if you know how to use this explicit formula, then what you can do is take your sparse matrix, whatever that may be, get a nice solver for solving equations with that matrix, use that for M inverse here, and then everything else you can just do directly. And all of these are going to be relatively efficient operations because inverse was in there. All of these are going to be relatively efficient operations because if you look at this M inverse L, L is like a vector or rank 10 or whatever, very low rank. So M is going to be n by n, but this thing is going to be some small number by n, so roughly linear size. Similarly, this thing is going to be very small, maybe 10 by 10. This thing is going to be linear size. This thing is going to be linear size. And you're dotting all of these together. So this is all going to be linear size stuff that we're working with here. We're never going to have to directly deal with any quadratic size stuff. So that'll all be fast linear-ish time operations, other than the M inverse solution itself. An even happier case, so a very common special case, is when this sparse part is not only sparse but diagonal. And if that's diagonal, then this is even easier because M inverse is trivial, right? You just have to divide everything by the numbers on the diagonal, and we're done. Great. So then you get the diagonal plus low rank formula, and again, it's very easy. You can compute that very efficiently. Similarly, if you're looking at, for instance, determinant, there's a similar formula for the determinant. You get determinant of M plus LR is equal to, again, I may not get this exactly right, but you can look it up on Wikipedia when you need it. I think that's it. And here, if this is a rank 10 thing, then this guy is going to be a 10 by 10 matrix, right? So you get your determinant of your sparse thing, M. If it's diagonal, then that's trivial. You're just multiplying out all the stuff on the diagonal. And then you've got this rank 10 matrix to take the determinant of instead of a rank million by a million matrix, right? So again, this is, you can look up these formulas if you need them. Look up low rank update to inverse or low rank update to determinant or what have you. Those are very fast. Eigenvalues are trickier. We don't have super simple formulas for eigenvalues, but there are some algorithms that can use a low rank adjustment to find eigenvalues faster than you would normally. They're just nice formulas. And again, Google all that. That's it for that. Back to it.
Should I ask a quick question?
Yes, I was just about to ask for questions.
Do libraries perform this stuff in the background anyway? If I give NumPy they'll solve stuff like this, does it just go yep, this pattern matches to low rank update, I'm gonna use this formula?
Good question. This in particular, it will almost never work.
Because it's harder to factorize the matrix that I give it into two lower rank matrices than
Yeah,
to actually just fucking do it.
Yeah, no, it's that it doesn't actually do a check for whether a matrix is low rank before it's doing things, or whether a matrix is a low rank component. If you are using a sparse matrix library in particular, then it will do some clever things like this. It still won't be able to handle this exact case because a low rank matrix is not generally sparse. You have to notice yourself that like it's a low rank matrix. But then you can represent it sparsely. The trick there is, so this sparse plus low rank thing is equivalent to a big matrix with some blocks in it. One block is your sparse matrix. One block is this tall guy. One block is this wide guy. And then the last block can just be an identity. And then this thing, this sparse plus low rank matrix, is a sure complement with respect to these. We talked about this a bit in the last couple lectures. Sure complement is basically what you get when you take a matrix representing some linear equations and you use these equations to eliminate these variables. So in this case, what we're saying is we have effectively some global variables and some global equations, and then everything else is local. And if we use the global equations to eliminate the global variables, then what we're left with is this sparse plus low rank thing. And the nice thing about this representation rather than this representation is that this one is explicitly sparse. Whereas this one will have usually no zeros in it because it just has lots of products of these. This one, most of the matrix is stuff in here. This is only roughly size n, this is roughly size n, this is roughly size n squared. So it is like explicitly a sparse matrix representation.
And what is the case where we should pay attention to that and like try to make sure that this computation is used instead of the one that is implemented?
The main case where you want to pay attention to that, basically whenever your numerics are slow and you're doing anything like an inverse or a determinant or anything along those lines, usually you'll have something like this somewhere in there. And if you can figure out what your low rank components are and explicitly leverage them, then you can make that a lot faster. And indeed, the standard libraries usually will not be able to do that. Any more questions on that?
Does CUDA do any of it for you?
No, this isn't a question. This isn't really a question of like how complete your numerical libraries are. It's just like not a thing that numerical libraries typically do. They generally expect you to have to recognize this yourself. Questions? Okay. One more thing I'm going to cover today. That was actually like the most central thing. Last interesting case of structure that you might run into, especially when dealing with correlations, analyzing correlation matrices. So let's suppose that I have a bunch of Gaussian equations. So like yi equals some linear combination aij of yj, and I'm going to assume that these equations form a circuit. So yi only depends on j indices which are less than I. So for instance, y3 can depend on y2 and y1, but it can't depend on y4. Right? And then each of these will also have some Gaussian noise in it.
It's like it's like triangular. Is that right?
Bingo. So as a matrix, this A matrix is strictly lower triangular. Upper triangular? I guess upper triangular, maybe depends how you draw it.
Yeah.
It's triangular is the important thing. All right, and then over here, I basically have identity times I. So overall, when I move everything to one side, I'm going to get is some triangular matrix times y equals Gaussian noise. All right. Let's pretend this is upper triangle. I don't remember which. Now, when I go to calculate a covariance of y, what's that gonna look? Well, I'll have expectation of y times y. Let's see, y is a column vector here, so this will be y transpose. That's going to be my matrix A inverse times epsilon transpose times A inverse transpose. Expectation of Gaussian noise itself gives an identity matrix. So this whole thing is going to be A inverse transpose, where A is definitely triangular, and the real case we're interested in here, sparse. So typically, the cases of interest are going to be when these interactions are sparse. Therefore, A will be sparse, but A inverse will not be sparse, so your covariance will not be sparse. So, how do I go back and get my sparsity structure out of covariances? Well, I'm going to invert this guy, right? So I take,
Isn't that like A transpose A inverse?
there you go.
And then you, because it's like triangular.
So this thing is A transpose A inverse. So if I take my covariance matrix and I invert it, then I'll have A transpose A. And if A is sparse, then probably A transpose A will also be sparse. In particular, the pattern I'll probably see is, for instance, maybe in A, I have a sparse row with like 3 entries in it, and then when I dot that with its transpose, I'm going to get something with 9 entries spaced out, with this being the diagonal. And then on this row, I'll have like, let's say I have 2 of that, and then that'll correspond to here, and there, and there,
Oh.
right? So on and so forth. So the point is, I'm going to get these sort of like scattered squares in my A transpose A matrix. And in the end, the important thing is if I have a linear number of non-zero entries in A, then I'm going to end up with roughly linear number of non-zero entries in A transpose A. Make sense? So main takeaway of all that is if you are looking at covariances in something that has like sparse interactions, then probably what you want to do is invert the covariance matrix and look for a sparsity pattern in that. Oh. Yeah. Those are all of the types of structure I wanted to get through today. Did anyone have any more questions?
Do you normally actually just like look at a plot of the matrix to do this?
Yep, that is what I normally do. Definitely the fastest way to see what's going on is like plot stuff.
So it seems like the last thing that you talked about just tells you whether or not A is sparse.
Mhm.
Why would I care?
Why would you care?
Like just the one bit of like, yep, A is sparse. You definitely got a sparse matrix there.
Well, if you look at it and first you see it's sparse, but more importantly, you can see the sparsity structure. So like you can see which things are interacting with which other things.
But it's A transpose A.
Yes.
So like, how are you gonna be able to disentangle like which things are interacting with what other things? And you get like A transpose A.
So as an example, let's say one of our equations is y4 equals y3 plus y2 plus minus. Then when we take A transpose A, the coefficients corresponding to this particular row, we're going to have 0, y1, 1y2, 1y3, minus 1y4, and then a bunch of zeros after that. When we take A transpose A, we're going to be taking an outer product of this thing with itself. So we'll get this. Zeros in this first column, zeros in the first row. 1, 1, this one, minus 1, 0. Dot, dot, dot. So notice here, your non-zero elements, you've got like a square block of non-zero elements.
Yeah.
And in general, it's not necessarily going to look like a block because like there may be some stuff in between here. There may be another column of zeros if this was something else. But the important thing is you're going to get like a sort of cluster of non-zero entries that are all like touching each other, right? So like this index, and this index all have non-zero entries between them pairwise.
Okay.
And that's like the characteristic thing you would look for here to notice that, okay, these things are sort of directly touching each other. They should all be in one equation somewhere.
Is there any way I can efficiently disentangle this so that I don't have to think?
There's probably multiple people have written code for it somewhere, but I don't know of like a very robust off-the-shelf thing.
Okay.
Any more questions? All right, I declare us done.